Ray, you're asking why not aim for the minimizer of the unconstrained problem, right? So I don't know anyone who does that, but one thing people do is take a Newton step instead of a gradient step, a Newton step direction. So Newton step direction is like, it's like you find the best second order fit to your function, the kind of quadratic fit of your function at your point, and you jump straight to the minimizer of the quadratic, or the direction towards the minimizer of your quadratic is your step direction. So that's the step direction used by XGBoost and used by a few other gradient boosting algorithms. So that's one difference from what we've presented. And then gradient boosting also introduces some different regularization on the size of the tree, and they build their tree in a way that's more integrated with the objective function. One thing to note about gradient boosting as we presented it is that the regression step, the base hypothesis space piece, choosing the H that fits G as well as possible, that's like a black box regression out step. So you can take any regression algorithm you want and do gradient boosting on it. XGBoost opens up that black box, and they kind of have more, the way they build the tree depends more directly on the objective function. All right. Now you should be able to read the slides and get the hang of it. All right. Try to make this last part go a little quickly. All right. So today we're going to talk about multiclass classification, partly like multiclass support vector machine and these sorts of things. So we've come across multiclass, I guess, 2 times. One, we had tree-based methods, which was kind of piece of cake for multiclass. And then the other was multinomial regression, multinomial logistic regression we talked about in the probabilistic modeling context, where we could handle multiple classes using a likelihood-based method. So what we're going to start with now is kind of a general approach to multiclass that will work for things like support vector machines and that sort of stuff. But the real reason we're talking about it is not so much for multiclass in the usual multiclass setting, but because the same infrastructure, the same kind of framework generalizes to the case of massive multiclass, like spaces of output spaces that are discrete but so large you couldn't even enumerate them. You could imagine, towards the end, if we have time, we'll talk about an example of sequence tagging, where you might have an input that's a sentence, and the output would be for every word in the sentence, what part of speech is it? And with certain settings, you could have something like 40 parts of speech. And if your sentence is of length 20, that's what, 40 to the 20th power possible labelings that you could have for a sentence. And this, you could think of that as a multiclass classification problem. But it's so massively multiclass that you can't really think of it as a multiclass problem. It's too large to handle with usual techniques. But what we're going to build up to as we do multiclass here will extend in certain situations to that sort of setting, which is the structure prediction setting. All right. So multiclass, input space X, output space enumerated 1 to k. And we've spoken about a few methods already, tree-based and multinomial. But today we're going to start with linear methods, back to linear methods, because they're always easiest to start with. We can always swap in other approaches later. And the main takeaway, as I mentioned, is that this will generalize to situations where you have exponentially large hypothesis spaces, label spaces. So what's the quick and easy way to do multiclass? This you might have seen already. I believe sklearn does this when you do logistic regression. It's called a reduction to it's a one versus all reduction. So the idea is that here you might have 3 classes, plus, minus, and O. And rather than thinking about this as a 3-class problem, we could think of it as 3 2-class problems, where each problem is, let's separate the O class from the other 2 classes, separate the minus class from the other 2 classes, and the plus class from the other 2 classes. Right? So we find 3, in this case, kind of separating hyperplanes. And then we find a way to combine them. All right? So we can formalize that as you train a binary classifier for each of k classes, and to distinguish like that one class from the rest. And so when we do classifiers, we usually get a score function, right? And so called h. And so our final class would be, let's run our k score functions, our k classifiers, on each of the on an endpoint, on the endpoint. Each one is going to be, the ith classifier, hi, will be positive if hi thinks that x is of class I and not of the other classes. Right? And so ideally, like only one of these k h's will be positive and the rest will be negative, and then it's kind of straightforward what to do. But some of these hi's might get it wrong, and so you might have multiple positives and then a bunch of negatives. So what generally people do is they use the fact that hi is a score, and maybe it represents kind of the confidence in the classification, and you'll choose the class that has the largest score. Right? If you're using real hard classifiers, plus or minus 1, you can you choose randomly or something among the positive ones. So the scores is more common. Is that clear? It's kind of the basic approach. You might have thought of it yourself. And it's nice because you don't have to invent anything new. You just reduce your multiclass to binary and you're done. You can use any binary classifier. All right. So is this enough? All right. So let's suppose we're in the linear setting now. So we have linear score functions. And just a little geometry review. So with a linear score function, if x is our input vector and w is our linear kind of parameter vector, how would you and theta is the angle between them. How would you characterize the theta for which we're predicting a positive class? If theta anywhere from negative 90 degrees to positive 90 degrees, you can do that very easily with a little bit of math, but it's pretty clear geometrically. So, okay. So one way to say that would be that the angle that x makes from w is smaller than the angle that x makes from negative w. And so you're kind of choosing the direction that is closest in angle. That's the intuition we'll use in a bit. So here's an example with 3 classes. And if we do the one versus all approach, let's suppose we're restricting our hypothesis space to linear prediction functions, which means they go through the origin. It's not affine, but rather linear. And so here's something separating 1 from the rest, and then here's 2 from the rest and 3 from the rest. 2 is interesting, though. We can't separate 2 from the rest linearly going through the origin. Because 2 is a relatively small class, it turns out to be better to label them all as negative than to give any weight to put any as positive with this, if your goal is to separate 2 from 1 and 3, which you can't really do here. So this is kind of an example of a failure of this approach, I think. So here's the decision regions, and kind of the discussion of theta was just to make it easier to explain that any given point on the input space is going to be classified by, so in the case that all these vectors w1, w2, and w3 are the same length, this is important. And to simplify, we'll say they're the same length, so it's easier to visualize. then our score for any given point is, our scores is W1 inner product with X, W2 inner product with X, and W3 inner product with X. Those are the three scores for the three linear score functions. And if the norms are all the same, say they're all 1, then the difference, x, norm of x is of course the same. It's the same vector for the 3. So kind of using the fact that the score is the norm of w times norm of x times cosine of the angle between w and x, you see that the scores are ranked by the angle between w and x. And so the class label is just going to be for any given point, say here, if you take the vector x, where is the angle smallest between x and each of these w's? I think it should be clear visually. If we didn't restrict to all being the same length, then it's a different story. Because if you made w3 longer, the inner product with w3 will be larger. And so it's going to spread out the region for that class. Is that clear? But if we restrict, if they're all the same length, then it's just whichever's closest in angle. All right. So how did 1 versus all do for this example? Not great. We completely fail on class 2. So it doesn't work so well. How do you see a way that we might be able to fix this? Yeah.
First we apply, say for the red we take out red, then if I just do the classification between the blue and green, then I can.
Okay, so this is a totally different approach. So you're suggesting let's do kind of a sequential classification where first I make a hard decision. Is this class 1, yes or no? And once I make that hard decision, then I am truly left with, if it's not in class 1, then I need to decide between class 2 and class 3. Yeah, that's a totally different approach to multiclass. That's right. OK. What else could we do? Well, OK, we could do a nonlinear. We could try to go nonlinear and carve that out in a different way. Yeah, so that might be the right answer. But it's not clear. It's not clear that it's not entirely clear that we need to go nonlinear to solve this problem. That's the question we'll come to. All right. So let's formalize what we have so far a bit. We have our base hypothesis space, which is what we're going to use to solve the kind of the 1 versus the rest problem, just linear. And then at the end of the day, we're predicting with a function that says, I'm going to evaluate my score function for each of the k classes. Each of those score functions comes from this base hypothesis space. And whichever is the largest, that's the one I'm going to go with as my predicted class. OK. So what's the action space here? Yeah, that's easy. That's just the k classes, discrete classes, no scores. This is just the final action space is just the intermediate. Yes, we dealt with scores, but the final thing we're predicting is just a discrete class. All right. So for this hypothesis space, which is from a bunch of score functions, choosing the one with the highest score, you could think of a learning algorithm as choosing a hypothesis from that hypothesis space. So here's the question. The fact that, and the learning algorithm we chose, the learning algorithm we are using to choose this hypothesis is we are building a 1 versus all. We're training H1, H2, all through HK as a 1 versus rest problem. And that's how we're fitting the H's. And that's how we're getting a function from this hypothesis space. So here's the question. So it's the learning algorithm that is choosing this final prediction function. And the question is it the learning algorithm not being good enough that led us to this type of kind of prediction failure? Or is it the hypothesis space itself? Or is it the case that there's no hypothesis in this space that allows us to predict this all correctly? That's the question. You think it's the hypothesis space. You think there's no W1, W2, and W3 that we can find that when we choose the class based on kind of largest inner product that we could get the right classifications.
So if you choose a different feature set,
Yes, so if you choose a different feature set, it's changing your base hypothesis space, which will certainly change your hypothesis space. Yeah. So with this hypothesis space, maybe choosing H's in a different way, not using one versus all. Can we solve? Yeah.
Change your loss function.
Could change your loss function in what sense?
Well, you could give more weight to correct answers than incorrect answers. If you did that, you'd flip the direction of W2.
Okay. Okay.
So basically, it's more important to get the ones from that space in your space than to.
Okay. So I think what you're suggesting is you can still do one versus all, but change the loss function you use, and then you might end up with a. So what you're basically saying is that the learning algorithm isn't good, because you're proposing a new learning algorithm, like reweighting losses for different types of misclassifications, and you're saying that you will end up with H's that work better. So your vote is for the learning algorithm being faulty. Okay. All right. So I sketched the following. So here's our three classes, and here's a proposal for three H's, or W1, W2, and W3. So does this work? Okay. So yeah, so any point in the blue region is closest in angle or has the largest score for the blue class. So this works. But these vectors do not solve any one versus all problem, right? So some other learning algorithm must have come up with these vectors, but it works. So it's not a failure of the hypothesis space, it's a failure of the learning algorithm. So in this particular instance, one versus all is not so good. All right. Okay. Especially constrained to having all these vectors being the same length. All right, so we're going to investigate this and see if we can come up with something that works better. So multiclass. We have our base hypothesis space of score functions. We're going to choose the one that gives the highest score. That's what we've got so far. And so one issue with the way we've formulated it is that it doesn't scale very well to a very large number of classes. Why? We have to somehow come up with a function for every class k. So if we're going to learn each function separately, and k is 100,000 or a billion or exponentially large, that's not going to work very well. So it turns out there's a reformulation that captures this as a special case, but allows us to scale to extremely large k. So here's how it looks. So we'll start with an arbitrary output space, y. It just only needs to be discrete. So same as we had before, really. And the main new idea is that rather than having a score function for each class, that would be k score functions, we now have one function, and we could call it a compatibility score function, that you give it, rather than just an x, you give it an x and a y, and it gives you a number that evaluates how compatible x and y are. In other words, how likely is y to be the label for x? Okay. Is that clear? So then what would a prediction be in terms of the compatibility score function? Argmax over y of h of xy for each x. Exactly, yeah. So this would be there. That would be a prediction. Now, do you believe that our previous framework is a special case in some sense of this? If I give you h1 through xk, there are kind of class-specific score functions that we're dealing with up till now, could you construct a compatibility function h for which the prediction function gives you exactly the same thing? So the way we did it before is you get h1 through hk. These are our score functions for each class. For any given x, you find the one giving the highest score, and that's your class. All right? So how can we define h of xy so that if we use that prediction function, we capture the same behavior?
Y minus h of x squared.
I think we could do something easier. You can use hi's in the definition of h.
Y becomes a subscript.
Say again?
Y becomes a subscript.
Yeah, y becomes a subscript. Yeah. All right, so the prediction function we had before, something called f1, is argmax over I of h sub I of x. Right? The form here is, it's called f2, is argmax over y h sub x comma y. So here y was in space y. Here I was in 1 to k. But we could change that like this. Now we just have to have a score function for every y in the output space. OK, so what do we do? How can I set h of xy to make these equivalent?
Put another weight.
Say again?
Put another weight.
Put another weight?
Put another weight. W H Y X.
Not necessary. What's puzzling you guys?
So they can be a summation of each simplified.
OK, so what if we just did this by visual inspection? Now, I know you guys are tired. It's like almost 3 hours in, so I will answer as a Perky student. So what if we have the argmax of y over y. What if we just did this? So h of xy. So whenever we plug in y equals 1, we go get h sub 1. Let's write that better. Right? Y equals 3, we get h sub 3. And we plug. All right. Is that clear? OK. All right. So, yeah? All right. OK. So this subsumes the other framework by just taking, h sub xi to be h sub I of x. We could, whenever we plug in a particular label y, we just look up the score function for that class and evaluate using that function. All right. OK. All right. But it also simplifies things. Yeah.
Just a comment, I think what tripped me up looking at this is that often when we see functions of x and y, it's like a loss function, L, like a loss of x, y. And in that context, y is the true answer. And I'm comparing the loss of maybe my predicted f of x to that y. And in this case, y means something else. Y is the set of all possible output classes.
Oh.
Just an observation.
Well, no, well, hold on. Let's drill into that a little bit. So, okay. In a loss function, you could say like y hat and y.
Right.
That's in this case where the output space and the action space are the same. Or otherwise, we had loss of kind of an action and the true label y.
Yeah.
Something like that.
Exactly.
But okay, it's this y is it's still a particular value of the output though.
I guess for one thing that trips me up is that I guess y is discrete, and therefore it's not defined for anything outside of that space, I guess. So it doesn't seem like a function, or a
Okay.
continuous function.
That's interesting. That's fair. Okay.
To rephrase it, in the h of x, y case, these aren't pairs of training. This isn't a training point, xi and yi. And often it is. I think that was
Right.
what I had.
Right. Really, you wouldn't see it that way, though. You'd see it as f of x, y, if that were a loss function. But yeah.
Yeah, true.
But I agree. Okay. All right. Well, now your horizons are broadened. And you can not blink at discrete functions of discrete spaces. And we're ready for h of x, y. It's not a loss. OK. Great. All right. But there's real advantages to going into this framework. In fact, I think you might want to use this in some of your projects, like for your matching questions. You want to look for like compatibility scores. OK. All right. So let's just put that together, the multiclass. So we have our base hypothesis space now is taking an x and a y and saying, how compatible are these things? How likely is y to be the label for x? And that's like a number. And then our final prediction function is going to just take the y that gives the biggest number. The learning problem is, yes, to find this function, but underlying it is to find a function here. So the learning problem is given a bunch of training data, find the compatibility score function on the input and the output space. Once we have that, we can just predict by searching over the y's to see which y gives the highest compatibility for any given x. Okay. All right. Great. Okay. So let's dig into the training a little bit by working out what would be a good compatibility score function. So given an h of x, y, we know how to do our prediction. We're going to find for any x the y that has the highest score. So let's suppose we want to apply h to an example xi, yi. All right. So h does well on xi, yi if the score it gives to xi, yi is large, because yi is the correct class. It's the correct label for xi. And in particular, it needs to be larger than the score it would give to all the y's that are incorrect. Because when we search for the y to predict, we're going to evaluate the score, the compatibility for every possible y, and choose the one that's the biggest. So we want to make sure the biggest is the right one. So correct if this happens. Is that clear? And so equivalently, we can say, we could put a max there. So we want the compatibility score on the correct label to be higher than the maximum score of the incorrect labels. All right. Seems reasonable characterization. And so what you could do is define the difference between these two things. And you might call it MI, so the difference between the scores of the correct thing and the scores of the highest score of the incorrect things. And you'll be correct. You'll get a correct classification if MI is greater than 0, right? Because then you're selecting the one that's correct, the highest one. And generally, you want that gap to be large to give you some buffer so that you don't make mistakes. So, so this should seem familiar. like we happen to call it mi, that corresponds to a correct classification when it's bigger than 0 and you want it to be large. So that should sound like a margin-based method. And so we won't define the margin exactly this way, but we'll in a bit come to a multi-class generalization of margin. But this is the intuition. Okay. So let's talk about linear methods with that type of framework. So now we have to introduce a new piece, which is a class-sensitive. I should have called this a compatibility feature map, which is if we want to make our compatibility function h of xy a linear function of something, we're going to need some features of x and y together, because hxy is a function of x and y together. So we need to featureize x and y, put that into a feature vector psi of xy, and then we have a linear function of that feature vector as our score function. Okay. All right. So kind of intuitively, you want this feature vector to extract all the relevant features, information for assessing how compatible y is with x. And then the final compatibility score is just a linear function of that. Then we, again, choose the argmax for our final predictions. All right, so how about this example again? Suppose in the original formulation we have 3 vectors, right? And so I've given some actual coordinates to those vectors. So the question is, how can we put this into our framework for the multiclass, for the compatibility function framework? Because there, we're going to need a feature vector of x and y, and then we're going to need one w vector. All right. Okay. So initially, our prediction function has all these wi's inner product with x1 and x2, and we need something of this form, a single w and a single feature vector, such that when we search for the maximum for y, it gives the same answer as this. Can you see? All right. So to do this, you just do a little bit of trickery. I think I put it on the slide, actually. So you can stack the w's together. You could say, all right, let's make one parameter vector that's all these together. W1, W2, W3. And then in that case, you need to make your feature vector mapping a little tricky. So when you plug in, you're making this function from x and y to the 6-dimensional vector. And remember, you're going to plug in one class at a time. So when you plug in class 1, we get this vector that's just x1 and x2 in the first slot and zeros everywhere else. So what happens when we take the inner product between psi x1 and w? We just get the inner product between w1 and x1 and x, right? And psi of x2 and w, we get the inner product of w2 and x, etc. So with this definition of the feature vector, we can kind of reproduce the inner product between w and the feature vector reproduces this inner product between wi and the original feature vector. So this is just showing how explicitly we can get this formulation as a special case of this kind of compatibility formulation. All right. Sorry, you guys are suffering here. You want me to go back? Well,
So how does this produce that W?
So I'm not claiming that this is not how we'll produce W. I just want to show that kind of this framework can capture the same solution that we had in the other framework. Well, I didn't say how to come up with W yet. But, I mean, it's just, we're kind of like comparing hypothesis spaces here. So we had a particular way to make our prediction function in this framework. And that came from a set of hypothesis spaces. I want to make sure that when we generalize to this framework, we can make the same sort of predictions. And one thing we have to figure out is what feature vector do we need to have to allow that. And this feature vector, this way to make the compatibility feature vector will allow it. So, all right, so an example. So this is part of speech classification. So input is a word. So input space is any possible word. And we've chosen like 6 classes for labels. And the features of X that you might want to use are like the word itself, like bag of words style, or ends in ly, yes or no, ends in ness, yes or no, these sorts of kind of word characteristics. And what we need to come up with, though, is features of X and Y together. So what would that look like? So here's a feature. It's a function of X and Y. So indicator, X is apple and Y is noun. All right? So that's a feature of an XY pair. All right? X is run and Y is noun. Let's see, what else do I have? X ends in ly and Y is adverb. All right? So each of these features is some function of the input X and the output Y. Clear? I didn't have, but I could have also put in like Y is noun or verb, or something like that. Just arbitrary functions of X and Y here. All right, so for example, let's evaluate that on a particular XY pair. So here's our feature map. So we plug in X is run and Y is noun. What's our feature vector? X is run. What's the value of this feature on X equals run? 0, because this is only 1 when X is apple and Y is noun. And this is run and noun. And so this is a 1, because this is true. And the rest are 0. So the feature representation for the input of X is run and Y is noun has a 1 in the second position and a 0s elsewhere in this example. All right. So, suppose we train the model on a bunch of examples. What would you expect the W1, W2, W3, and W4 would be corresponding to these features? Positive. All right. So, so first of all, when would you want a coefficient that's positive on any particular feature? If they're likely to occur together, right? So if this were so run and noun, yeah, a run can be a noun, so that should have some positive weight. Run can be a verb, certainly, ly. So all these seem positive. We could also have negative ones in here that would deserve kind of negative weights. So the weights would, when you take a linear combination of these things, it's supposed to assess how likely Y is to go with X. So in that situation, you'd want features that support that compatibility to be large. Okay. All right. So suppose we have learned a particular W using some method we still haven't specified. And then to do the prediction, we would just plug in, if the input is apple, for instance, we plug in all the possible labels and evaluate the score functions on each of those. So we'd find the features and then the scores for each of those, and predict the label that gives the highest score. All right. So in this setting, every label kind of showed up explicitly. And this is, now we're kind of getting to the main point of this whole setup. This is kind of the crucial new idea that we're allowing with this framework, which is that what if we have a huge number of classes? And the idea is, let's make features of the classes and not just of the x's. So before, features entered in explicitly. Does y equal noun? But for certain types of spaces y, it makes sense to featureize the labels themselves. So here's some example. Suppose we're doing advertising, right? The input is a user and kind of a user context on a certain web page or something like that. Maybe we have information about the user. We have plenty of features describing a user, right? And then we have this potentially huge set of banner ads that we could show to the user, right, on their web page or on their phone. We want to match them. We want to find an ad that would be relevant to the user in some way. So this could be a classification problem, but you may have like a class size of 1 million or something. And the truth is that each of these ads, they're not all so different. Like a lot of these ads might be quite similar, and it doesn't necessarily make sense to kind of treat them all separately. So here's an example of a feature that we could use that kind of captures this idea of kind of generalizing across classes. So we could have a feature that says it's a 1 if X is interested in sports, so we have some description of the user that they're interested in sports, and Y is relevant to sports. All right. So the Y relevant to sports part, that's a featureization. That's in some sense featureizing the label itself. We're noting that this, banner ad number 375,000 is relevant to sports. It's a characteristic of Y. And we can put that into this feature vector. So rather than having to have a separate feature for every single banner ad that's relevant to sports. Here's another one. User X is in the target demographic group of ad Y. So maybe the advertiser specified what type of person they're trying to target, and we know something about X, and we could just have a feature, are they compatible in that sense, yes or no? All right. So this is a pretty powerful framework because we can have features that pull out information about X and Y and directly do kind of a little rudimentary measure of how compatible they are. And eventually, these would all be put together with some linear combination or some more sophisticated function later. But the key step is these features that work on X and Y in a more generic way, more general way. Okay. All right, any questions?
So is this like a classification explanation of recommender system?
This would, OK. So how does this relate to recommend?
Yeah.
Well, we're still in the multi-class framework.
Right. But this looks like a recommender system problem.
Yes. Well, is this a recommender system? Yeah, maybe rudimentary recommender system. Yes.
Is this feature space just a sparse representation of the feature space which we used before?
Is this feature representation a sparse representation?
I mean dense.
Dense representation. What do you mean by the feature space we used before?
The one on the previous slide.
This one? Well,
Because we are just getting rid of the zeros, that's it. Else it's the same.
no, the zeros are still there. I mean, OK. Yeah, so OK. I think I understand what you're saying. So you're saying for any feature I write here is some kind of, you could write this as a union of for every single user X that previously clicked, for all the companies that sponsored. Wow. Let me think if that's true. I mean, I think so. I mean, I guess you could always write any feature and break it down into pieces. But it's not sparse dense. It's because, like, if you broke this into pieces, then you'd have a separate feature for every possible. OK, so here's the simplest example. All the banners that are relevant to sports. So there's like 1,000 banners relevant to sports. So yes, you could make 1,000 features for X is interested in sports and Y is banner 10 and Y is banner 11. And yes, you could make 1,000 features. And if you added those up, you would get this feature exactly. But if you left those features in, you now have 1,000 parameters extra, one for each feature. So it's not really the same. Representationally, this is more limited, actually. But hopefully, it's easier to work with. Yeah.
With this high, when K, the class is very large, is that blurring the regression versus the classification in a sense?
So when K is very large, does this kind of get us closer to a regression setting? I don't think so, because in regression, there's this very specific kind of relationship between Y's. And it makes sense, for instance, to measure square distance between Y's. And we don't yet have any way to measure distance between Y's.
And these look very arbitrary. It's like rule-based, this kind of.
Yeah, these types of features look very arbitrary, as features do. Yeah.
You can design the feature for the Y. Now something you can measure Y's, distance between Y's, let's say dot product.
Okay, so you're saying we could think of that as embedding Y's into a Euclidean space in which things like dot products might measure something like distance, semantic distance between the Y's. Yeah, absolutely. That would be very interesting. And then once you're in this space, maybe you can use some kind of higher dimension regression. We didn't talk about regression in like RD, but why not make your loss function like the sum of squares of distances between the higher dimensional label space? Yeah, OK. So if you can embed Y into some Euclidean space, maybe you can use a regression style technique if your embedding is good. That's interesting. Yeah. All right, I'm just going to go a little bit further. Any questions on this? All right. So the last thing I'll talk about is just to give you one concrete loss function for this case. We haven't actually spoken about the loss function that you would use in this setting. So far, the only actual learning algorithm we have is one versus all, but we're ready for something a little more. So this is the linear multi-class support vector machine. And what we're going to do is generalize margin. So if H is our compatibility score function, we could define the margin between the correct class and any other class in this way. So on the ith example, xi or yi, we look at the difference between the compatibility of the actual label with its input, so xi and yi, and look at the difference between that and xi and for some other y, for some other label. And so we could write that m sub IYH. So in other words, for compatibility score function H, on the ith example, what's the difference between the compatibility score given to the correct label and some other label y? All right. We're going to end up selecting the y that has the highest score. So we want the correct label to be larger than any other label. And so we want this m sub IYH to be large for every y for every I, at least for y not equal to yi. All right. So if we plug in this linear score function with our feature map, it comes to this form. And so we kind of want to maximize this m sub iy. And one way lots of different ways to do that. Because we have several y's for each I, so kind of how do we So we have a bunch of numbers we want to be large. So how do we handle that? So kind of take inspiration from SVM. So in SVM, we have, this is our objective function. And we could think of, we have our margin, which we want to be large. And this one we could think of as like our target margin, right? Because once we got to margin of 1, we don't penalize anymore. That's what this is doing. All right. So what if we took multiclass SVM like this? We have the same formulation. The only thing that has changed is that for the margin, we have a margin now for every other class Y. And we say, all right, what's the worst case margin? Or what, this is the loss on a particular, sorry. So for a particular alternative label and a particular prediction, we have this margin MIY. And then we're kind of evaluating how good that is by plugging it into the hinge loss. So we're trying to get MIY to be greater than or equal to 1. So we have the loss for each of our margins, 1 for each possible class label. And then we say, all right, what's the largest loss for an incorrect answer? And that's what we're trying to minimize. This actually, by making this more general, it maybe gets more clear what's happening. So let's introduce the fact that when you have a multi-class, not all errors are the same. Like some are worse than others. And so we can introduce, rather than 0-1 loss, let's go with this more general loss that for any label Y and predict action, so predicted label, we're going to allow an arbitrary number that we write down by hand. We decide in advance, kind of, for the confusion matrix of possible predictions and true values, how much do we want to penalize each? So that delta we can call that the target margin. We can use that as the target margin in the multi-class SVM. And so the idea would be like, for a really bad misclassification, if it would be really bad to misclassify something as a particular label, you ask that the margin on those be larger. And the ones that don't matter as much, you can have a smaller target margin. So that's what's going on here. We've plugged in, instead of 1, we've plugged in delta for the particular pair of true class label and predicted class label as the target margin for this margin to attain. All right. All right, this is the last math I'm going to show you.
So for this math, you want to make every Y to perform well.
So first of all, this is a sum over examples I. So I refers to the ith example. And any Y, because you're concerned about Y not equal to, you're saying why isn't that Y equal to Y not equal to Yi?
Right. I mean, now even if,
so it should be the same, because if Y is equal to Yi, then the margin should be, what's the margin going to be? 0, because we're, OK. And then, presumably the target margin, the loss for a correct prediction should be 0. Unless we define delta in a silly way, it'll be equivalent. Because if it's the same, this will be 0, this will be 0, this will be 0, and it won't be the max. Yeah. OK. All right. So here's the question: Is this framework we developed for multi-class, is it actually useful for doing multi-class classification? I've argued the main reason I'm presenting it is because the framework is nice, that it allows you to generalize to huge spaces, of output spaces. But if we actually consider it as a classification method for 10-class problem or something, does it actually help us? And there's been some good investigations of that, comparing one versus all to the kind of, for instance, this multi-class SVM. So one versus all, we gave an example where it fails for simple linear classifiers. So, is that a fatal flaw or like a carefully constructed kind of trivial example So is it typical or not typical? And there's this paper from some time ago called In Defense of One versus All. And they reran all these experiments that people had done that were promoting things like multiclass SVM and similar, more elegant maybe solutions, elegant solutions that are maybe more elegant than this one versus all approach. And what they found was that one versus all works basically just as well in practice as long as you are using a sufficiently powerful hypothesis space. So not just plain hypotheses, they were using SVM with RBF kernels, right? So RBF kernels can have very nonlinear prediction functions. And if you were doing that, and if you were tuning appropriately, then, granted, they were working on some relatively small data sets, but they found that one versus all worked just as well, at least as well as the multi-class versions. Just for kicks, they also, instead of one versus all SVM, they did one versus all for square loss. I don't know if you remember all the way at the beginning, we said, well, what happens if you use square loss for classification? Seems a little silly, but doesn't necessarily mean it doesn't work. And they found it worked also just as well. Okay, so that's some empirical support for that. Okay. All right. And so the takeaway is that the reason we went through this path is because it generalizes to k very large, and in which case one versus all would not be tractable. You can't do one versus all when k is 100,000 or a million or something. All right. So let's end there.